Okay, so this rate law question looks a little bit different than the one that we've seen before. What's different about it?
It's not a number that's below the decimal.
Okay, anything else? Concentration's greater than 1.
The rates in moles percent.
So is it rate? It's in seconds, right? Moles per second, rate time. These are a lot bigger than we've seen before. Everybody okay with that? So why would it be a lot faster? Maybe.
Spontaneous.
Say again?
Spontaneous.
Yeah, they were spontaneous. Same thing. The first comment. What was the first comment? What did you say?
They're bigger numbers though. I don't know that they weren't decimal.
They weren't decimal numbers, right? So those decimal numbers, we were looking at like 1.6 times 10 to the negative 4. Is that very concentrated? No? So these are numbers greater than 1. The other ones we were talking about things are several decimal places less than 1. So do these rates make sense then? What's one of the things that can increase the rate of a reaction?
Concentration.
Increasing the concentration. Well, 4.5 is thousands of times more concentrated than some of the things that we've seen before. So what would you expect the rate to do? Go up a lot. So that's what's happened here. All right, so we'll pick trials number, so no change here, 3 times here. How much did this go up? 9 times? This goes up by 9. And so 3 is equal to 9 when it's squared. So it's second order with respect to the oxygen. And then we're going to go here to here, and that's 3 times. And here to here, and that's 2 times. And here to here, and what happens there? 108? Yeah, that sounds right. 108. All right, so I've got 108. How much should the rate have gone up because of the oxygen?
Twice.
4 times? Yeah, because it doubled and it's second order. So 4 out of this. So what happens if I divide the 108 by 4? What do I get? 27. Okay, so that means that the hydrogen concentration change has to be 27, has to be responsible for that. So when is 3 equal to 27? When it's third order reactant. We okay with that? Okay, so I've got K is equal to 580 divided by 4.5 cubed times 2 squared. So 580. $1.59. So 1.6. So then rate is equal to 1.6 hydrogen cubed, oxygen squared. There's your rate law. If I add calcium metal to a solution that contains iron ions, will any reaction occur? So if I add calcium metal to a solution that has iron ions, do I get anything out of that? What's the one time when a reaction will happen with these?
If the iron is an iron and the other one is an atom, one wants electrons and the other one wants to give away.
Okay, so the one that wants to give away has to have its electrons, and the one that needs the electrons has to need electrons. So how do I know which one's which?
Look at the chart.
So is calcium above iron on the chart? It is. So calcium has its electrons, so it could give its electrons to iron, and since iron's lower and needs it, then yeah, a reaction's gonna happen. So we're gonna end up with calcium plus iron solid. And that would need to be balanced with 3 of these and 2 of those. If I add magnesium metal to a solution containing sodium ions, okay, so I've got magnesium metal and I have sodium ions. Is anything going to happen here? Nope. Magnesium won't give electrons to a needing sodium because it's lower on the list. Draw a galvanic cell of nickel and metal, also give a shorthand notation and the voltage. Okay, so I'm going to put an ACL in there and then magnesium and nickel. I'm going to put nickel ions in here with some nitrate. And I'll put magnesium ions in here with some nitrate. Which direction are the electrons going to travel? Towards the nickel. Okay. So electrons are going to go that way. And the shorthand notation for this is going to be magnesium solid is going to turn into magnesium ion. And nickel ion is going to turn into nickel solid. So if I look at the table, the nickel, sorry, the so our nickel, is this happening to the nickel? Is the nickel gaining 2 electrons and turning into nickel solid? It is. So we're going to use that negative 0.23 volts. So negative 0.23, sweet, 23 volts. And then I'm going to add that to 2.38 volts. Because if I look over at this table here, we're going to see the magnesium is here, and it's negative 2.38, but it's written backwards. So I swap the sign. And so then I end up with, what do we get here? 5. Not pleased. 2.15 volts generated. Is that it? Is that all we asked? Which substance was oxidized? The magnesium metal was oxidized. Which substance was reduced? The nickel ion was reduced. Okay. Phosgen, write a balanced chemical equation. I feel like I wanted a follow-up question with that one and forgot to write it. Pick two metals in an activity series, write down the initial conditions for a spontaneous reaction to occur. Write two more where no reaction would occur. Okay, so give me a metal. All right, that one's easy. And another one?
Zinc.
Great, okay. So I've got lithium and I'm adding it to zinc. What condition does the lithium need to be in for this to be spontaneous?
Atom. Has to be.
It needs to be an atom, so it's a solid. And what condition does the zinc need to be in? Not an atom, so an ion. Cool, so that reaction is going to happen. So when would it not work? If lithium was a solid and zinc was a solid, nothing's going to happen. If lithium is an ion and zinc is an ion, nothing's going to happen. So this one, no one needs electron, and this one, no one has electrons. Right, equilibrium expression for that. Okay, so K is equal to CO2 squared divided by CO squared O2 not squared. Calculate the equilibrium constant for these amounts. So K is equal to 0.032 squared, 0.025 squared, 0.0016. So 0.032 squared divided by 0.025 squared divided by 0.0016. So I get 1,024 for my K. Which, what does that indicate if the K value is 1,024? Say again? Nope, that is not what that means. This is nothing to do with delta G. A K value that's really big means the numerator is large, the denominator is small, so that means I've got a lot of product that I don't have very much reactant. It's still in equilibrium, it's just that the equilibrium is really skewed towards the product side. If you add hydrogen to this, how will this reaction shift? Okay. What's going to happen here? I increase the amount of hydrogen, and which direction is this going to shift?
Right.
To the right?
No, left.
To the left. So for this one, it's definitely going to be shifting that direction. So for the next one, if I remove acetic acid from this, so I take out some acetic acid, what's going to happen? It's also going to shift to the left. So the second one happens because the reaction replaces the lost acetic acid. Why does the first one happen? It removes extra hydrogen ion. It's trying to get rid of that. I put H plus in, it's like, all right, there's too much H plus. Combine it with the acetate anion to remove it from the equation.